When discussing links, there really are three things we need to talk about. The first one is this concept of an inode number. What happens when you create a file, and we'll just say that's a spreadsheet, or a folder? And really, you'll hear this, a folder is just some kind of a fancy file, because you'll hear the term that everything is a file in Linux. It gets confusing, but just keep that in mind. Some people may refer to even a folder as a file, and that's perfectly legitimate. When you create either of those, we give them names, pretty names that we can identify. So the sales folder, the June spreadsheet. But the system doesn't track those objects based on that name. It tracks them based on something called an inode, a number that's associated with that file folder. So we're going to look at that first. After that, then we'll come back and take a look at a hard link. Hard links are a little odd. You don't really use them very often. The file system uses them. The file system requires them. But they have a lot of limitations. And so more than likely that's something that you'll come across once in a while in your career. And on the exam, I doubt you'll have to deal with them. What you may have to deal with, and what you will deal with in the real world in your career, is this concept of symbolic links. Once again, as I mentioned previously, when I say symbolic link, you can think of a shortcut in a Windows kind of desktop or a Mac desktop, right? They really, functionally, that's what they are. But they're also called soft links. You'll probably never hear them called shortcut except for me and a few other people. Most people will call them either symbolic links or soft links. So the first thing we'll look at is this concept of an inode. We'll go take a look at that. So let me close this out here. I'll minimize that. Bring up my Red Hat 9 box. When I create, I'm going to get to my home directory here. And I'm logged in as root right now. When I create a file, let's see what files we have in here. We do have a couple. All right, well, so we'll just stick with file 1. So let's just look at one of them. Well, actually, let's look at all of them, and then we'll narrow it down, and I'll also explain what's going on here. So you know the ls command will list the contents of a directory. The L part of ls will put it in a long format like you see on your screen right now. And if you remember earlier on when I was talking about the various options that are available, I pointed to the inode or the I option and said, we'll talk about that later. This is that moment. If you put the I option with the ls command, it will display the actual inode number of that file. So I'll do that. Let me clear my screen so it's a little bit easier, and I'm going to make this a little bigger. Press enter. There is file 1. Now remember, file 1, it's an empty file. I created with the touch command. There's nothing about it special. When I created that file, wrong one. I named it. I gave it a name. The system at the moment of creation stamped it with a number. That's what the system tracks it by, not the name. The easiest way to show that to you is I'm going to rename it. Once again, this is a good description of why you can use move to rename things, because the fact is, if you're not moving something to a different partition, then you're not moving it at all. Even if you move it from one folder to another folder, right? So we have two folders here. If I move that file into the books folder, it's not really moving. It's just changing the path in the file allocation table to that file. Same thing if I moved it over here to hard link. It's not going to move it anywhere. It's going to stay in the exact same spot it's on the disk. The data, I'm talking about, the data. It doesn't move. The only time it will actually move is when you tell it to move to a separate partition on the same drive or a different drive, right? Just different storage places on your system. That's when move will actually pick it up and put it down again. That's what move will do. But when you're moving within the same partition, and we are doing that here, we really wouldn't move anything. It would just change the path. That whole description of where that absolute path would just change in the file allocation table. But the actual data would stay in the same place. If I was to rename this file, so here is the number, just remember the 1715, right? That's the easy part to remember, that number. 1715. If I was to rename it and say file 1, and we'll call it new file, and then I do an ls-li in here again, and I press the enter key, you'll notice the number associated with the new file, I change the name, it's the same number. It does not change. Everything is tracked. Computers use numbers. I'm sure, think about, the easiest way to think about this, I think, is your phone. You know how you can pick up your phone and auto dial, hey, call Bill, call Mom, call Dad, and it dials out the number. Well, the name just links it to the number. The name is so you don't have to remember the long number to dial that thing. And when you tell the phone to call that person, it has to match that name you've just used to a number. Same thing happens on websites. When you type something like www, let's just say redhat.com, and press enter in your browser, that name, that's just like the contact on your phone. That's for us. I can remember that name. I can't remember the number that I need, which is an IP address to get to that. But when you press enter, as long as you have DNS set up on your system, you press enter, that name is then resolved to an IP address, and that's how you connect to that device. So computers use this concept of names all the time. Oh, numbers all the time. Names are for us, for humans. Even the user accounts. Right now I'm logged in as root, and if I type the ID command here and press enter, what you see is, notice this, my user ID, that is the number that is associated with the root account. And on every flavor of Unix, from Unix, Linux, Mac, it doesn't matter, the root account is always number 0. All right, we're going to talk about that in a second. Every account I create on here, so if I ask the system what is student's ID, it's going to come back and say student is ID 1000. That is how the system tracks us. That is, notice, root, the name root, it's in parentheses, like it's an afterthought to the system, because it is. The name is for us. The system tracks it by the number 0. As a matter of fact, later on when we get into users and groups, I'll demonstrate how no matter what account on this system, if you give it the ID of 0, it becomes root, and it can do anything on the system. It's crazy, right? But that's true. So this concept of an ID for user accounts, or when we're dealing with the file, an inode. So everything gets an inode number. Every file, every folder that we create gets a number, and that is how the system tracks that particular number. So just to show you how important inodes are to the file system, I am going to display my current storage on this machine using the df-h, that stands for display file system, -h is human readable, and I'll press enter. Don't worry about what you see on the screen, we'll be talking about it. Notice /dev/sda, that is a partition that is mounted in /boot. That partition's total size is roughly about a gig in size. I'm using 359 megs, which is about 36% of the storage available on dev-sda. Down here, dev-sdb is a tiny drive. You can tell it's really small. It's only 3.8 megs. Easy to demonstrate. Basically, you can see from here that I've only used 1% of the total storage on there, so pretty much nothing. If I want to see storage from the perspective of inodes, right? So every one of those items that are stored in /dev-sda in boot has an inode number associated. Every time we create a file, it gets an inode number. Doesn't matter how big the file is, how small the file is. None of that matters. If I type ds-h and add the inode-i option to it, and I press enter, you can see that we look back at boot where it said it was 36. It's still here. 36 100% used. As far as the inodes are concerned, I'm using 1% of the inodes. The reality of it is that you're very likely to run out of storage blocks before you run out of inodes. And we can see the total number of inodes available to us here. So 512,000 possible inodes, so 512,000 individual files we can create. We've created 366. Now here's the thing. If I go to 513 possible files on here, that would, even if it was the rest of the files that I was making on here were all empty, it would stop me from being able to save anything because it's run out of numbers to associate with the files that are being created. This is how I'm going to demonstrate that for you. Notice that right now on dev SDB it's mounted in /mount or MNT, that's what it's an abbreviation for. If I was to touch a file, well, let me CD into there, MNT, and what I'm going to do now is touch a file in here, and we'll call it file 1. Press enter. I'll do a df-hi again. Up here I had used a total of 11 inodes, and now you can see I created another file. Now I have used a total of 12 inodes. What happens when we run out of inodes, right? That's a good question. So on this particular file system, since it's only a tiny little thing, if I was to create 1013 files, empty files now, right? Touch command is just making empty files. There's nothing on here using up any real space. I'm just consuming inodes by creating these empty files. If I do that, and I can do that by running the touch command, I'll put the prefix file there, and then this is what I'm doing right now is called brace expansion. You're going to love brace expansion. Actually, there's an opportunity to use brace expansion in the lab that's coming up in chapter 3. If I was to say I want to create that 1013th file, what I can do is start at 2, since we already have file 1, ... and go to, we're going to go to 1015. And then close it. So this, what you're seeing here is called brace expansion. We'll be talking more about it in the upcoming lecture. But basically what's happening, the touch command, you know what that does? It just creates a file. The name of the file is going to start with FILE, and then it's going to create FILE2, FILE3, 4, 5, 6, all the way up to 1015. So it's a great way to create a whole bunch of files. Actually, I'll show you something like this again when we go to actually play around with globbing. And I create this, what I call a playground that we can play in. So here I go. I'm in the mount directory. I'm going to press enter. And what happened? Device, no space left. So we can do an ls-l in here, and you can see there are all the files, and if we scroll all the way up to the top, right, it'll stop right around 1013, right, somewhere around there. There goes 12, 13, done after that. Let's go look at it from a storage perspective now. dh-h. If I look at it for blocks, remember this is the stuff we normally think of when we think of storage. I've only used 40K of the storage. I still have, as far as this disk, 98% of this disk storage is available to me. But I've created so many empty files on here that I've now run out of inode numbers. And if I type df-ih again and press enter, right down here you can see how many free inodes are there? None. How much have I used? 100%. By running out of inodes, the file system cannot associate a number. Remember, it doesn't give a darn about the name of these things. It wants to assign a number to the files that are being created. I used all the inode numbers. They're all gone. It doesn't matter that I still have 98% of the free space on this device available to me. I cannot create anything. Now, we can get rid of those. I'll use the rm-f command that you've seen me use before, and I'm going to use a wildcard because we will be talking about wildcards. You saw it when I scrolled off the screen back up here, right? It's a list of things. So I don't want to have to individually type those in. And even easier than using any kind of brace expansion is to just put the asterisk there. What that says is remove anything in my current location, and my current location is MNT. Remove it, anything that begins with F-I-L-E, and I don't care what comes after that. And I know the only thing in here right now are empty files starting with F-I-L-E and then some number after that. So if I do that and then do a df-ih here again, and I bring it back up, you can see we're back to where we expect to be. We've only used 2% of the inode, so now we're back to our normal way of looking at things. We've used 2% of the storage and 2% of the inodes. I'm sorry, I lost that one there. So that shows you how important inode numbers are to the system. The next thing we're going to look at is this concept of a hard link. And this idea of an inode really comes into play with hard links.